So has anybody ever, who here has done dissimilar welds? Has anybody else made dissimilar welds? Yeah, they're fun to make, but you're always going to have a transition region, and there's almost always something you need to worry about because you're mixing those elements there, and you got to be careful what's going to segregate. So this, and I'll show it in about 3 more slides, the martensite layer more vividly, but it occurs in the transition region, this hard, brittle martensite layer because of that transition and composition. So for friction welding, we didn't know. Nobody's looked this close at this dissimilar friction weld, so we didn't know if we were going to get martensite or not. And we do, but at the inner location, so the close to the center line of that friction weld, it's a very thin layer, very thin wispy layer, and the transition region is very abrupt because we never turned it into a liquid. We put a solid to a solid, it heated up, there was some diffusion, we formed a bond, there was a little bit of mixing, and there was enough to get this little bit of martensite, but not much. However, at the outer edge of the friction weld, there's more mixing. You've got those two pieces closer to the periphery, there's more rotation, and there's going to be more heat and more mixing in the solid state weld. So there's more of this martensite, and you can see it kind of has an interesting interspersed layer kind of morphology to it. And there's more of a transition zone, but again, it's interspersed layers. So if you've done dissimilar welding, okay, has anybody heard of the Schaeffler diagram? Schaeffler diagram. Okay, we've got fewer. It really helps with dissimilar welding. What you do with Schaeffler diagram, if you're welding a plain carbon steel to a stainless steel, it can really help you predict weld cracking. Basically, you take your elements from the composition that you have, the composition report, the spec report from your material. You plot that on the nickel equivalency, and then you take those elements that are more of what we call a ferrite former, and you plot those on the chrome equivalency. And so here I plotted 1018 and the composition for 304L bar and 309L all weld metal. And a Schaeffler diagram is kind of a non-equilibrium phase diagram, okay? And a phase diagram just tells you what phases you're going to get when you start combining elements. Okay, so this is useful. It was made for welding dissimilars. You can find a lot of model Schaeffler diagrams on the internet if you're going to do some cladding, and it will help you know if you're going to have cracking. So I took those EDS spectra, those lines that I showed you, and I plotted those here in the Schaeffler diagram for my all weld metal. Okay, this segregation makes kind of a shotgun plot here. Gives us all sorts of from ferrite phase to austenite phase, okay, and then at the transition zone, some austenite plus martensite. So, and then for the blue here, I did the same thing, took those energy dispersive spectra locations, and I plotted those, so it forms more of a straight line. Okay, there's no segregation in a solid state weld, so that's where there's a straight line here, not as much of a shotgun plot. So for a solidification weld, here's one way that you can use a Schaeffler diagram. If your composition that you plot between your two metals you're putting together, if it falls in this austenite, you might be concerned about solidification cracking. Of course, it depends on how much clamping you have and your cooling rate and some other stuff, but solidification cracking, not an issue for solid state welding, for inertia friction welding. And then down in this martensite, more what you have to worry about is brittle or cold cracking, or maybe hydrogen cracking with that martensite structure. Okay, possibly less of an issue for the solid state weld. And the last two slides here, I'll show you why I feel like it's less of an issue. I have yet to test it, but I feel like it's going to be less of an issue. So another fancy schmancy tool that we have is electron backscatter diffraction, which is a tool that also works in a scanning electron microscope. And what it does, it gives us pretty maps. It's a little bit small here, maybe if you're in the back, but pretty maps of the phases that are in our metal. So this is the fusion weld. From the 1018 steel to the weld cladding, you can see this martensite layer in the partially mixed zone. And if I separate out the phases and look at individual grains, I see that these austenite grains in my weld, so weld grains can be fairly large. It's a solidification structure, so they're pretty big. So there's two takeaways here, two key features. One is for the fusion weld, there's a continuous martensite layer, and two is there are coarse austenite grains. However, for the friction weld, I've zoomed in more here. Maybe you can't see the scale bar very well from a distance, but these are much finer grains. And I've circled a couple grains here, A and B, and that's where some of these austenite grains, because of the mixing, partially transformed to martensite. So there's the same two key features here. The martensite layers in our solid state weld are much finer, 1 to 3 microns, and the austenite grains are 5 to 10 microns. So if I go back, whoops, 50 microns and 80 microns versus 1 to 3 microns and 5 to 10. Generally, a fine grain size gives us better properties, it gives us better resistance to hydrogen cracking, gives us better bond strength. So if I summarize the whole talk here, what have I done so far? Optimized those inertia friction weld parameters, compared the mechanical properties and the microstructures of the solid state weld, the friction weld versus the fusion weld, and shown that this interface is different. That in friction welding, the interface is narrow and discontinuous, more of the layered type of interface, and it's also fine grain. So here's the large fusion weld interface, here's the fine inner friction weld interface, here's the outer one, which is, again, the morphology is different and more fine grained. So the big takeaway is that solid state cladding may outperform fusion cladding if we can figure out good application processes, a good way to apply that mechanical deformation at the same time as we do the heating. So it's possible there's a good application space for solid state welding and cladding. Here's the future work that I have planned. I'm going to compare the formability of those fusion welds and friction welds. I'll do some stress corrosion cracking, because from the video I showed, you see that corrosion is paramount. So we need to see what the corrosion performance of these, how they compare of these two cladding application methods. I'm going to move one step further toward the idea that we can make tubing using solid state cladding. Take that concept one step further using our patent idea, and then some finite element modeling. So with that, I'll just go ahead and I'll be finished. I'd really want to thank the American Welding Society for their fellowship, for supporting this work. Obviously, I wouldn't be able to do it without the scholarship that I got from AWS. And the Colorado School of Mines, both the professors, they're outstanding, and the students that I've gotten to work with and learn how to weld and operate equipment and all that stuff. I've learned a lot while I've been at the Colorado School of Mines. So with that, I'll take any questions. Got any questions? Yeah.
I got several questions. Number one, maybe three. Number one, when you do that friction welding, how do you prevent work hardening in the stainless steel?
It does work harden. Yeah. You can see that. I think I glossed over it, but you can see that in the hardness and the hardness map.
So it does work harden?
Yes.
And that answers that. Next question.
Yeah.
Is that actual fusion process, or is it an adhesion process?
Define.
Fusion. Is it a fusion process?
It's a solid state welding process. So.
Okay. You get in the same problem with friction stir welding because you're doing something in the material that makes it almost behave like a liquid, but it never gets to the melting point. So
does that make it adhesion? If it was adhesion, I think it would pull apart when you touch them.
I want to call it a non-fusion welding process. I'm in front of my professors though here, so I don't want to say something wrong and get quizzed too much. You see here this strain hardened area here?
The interface.
Yeah, close to the interface. Even though it was high temperature, it still did exhibit some strain hardening there.
The other fundamental question I don't understand. On the right side up there, you got 304L. On the left side, you have 304L.
Yeah, 304L.
You have 1018. 304 is an ASTM or ASME designation grade for an ASTM classification. What's 1018 do? Is that an ASTM? No, I'm familiar with ASTM.
No, AISI, thank you. I didn't remember who it was.
So you're mixing and matching specification standards, metal standards?
Yeah.
That's incorrect. AISI classification 1018, AISI 304, stainless steel, those are all AISI. But ASTM will put part of those classification and has their own classification. So no, he is not mixing those.
Okay, well, is there an ASTM classification for the 1018 steel?
Oh, probably. For example, ASTM, you have the A something.
836 is mild steel.
Right. So that, but there's a distinction there is that the AISI grade, for example, is more based on chemical composition, while it's ASTM, those grades, many of those are based on mechanical performance or property.
Both chemical and mechanical?
No, it's only the performance requirement. Then you tack on the composition to it, but the first requirement is a strength requirement.
So when you look at an ASTM designation, they give sometimes fairly large composition ranges, whereas if you look at AISI designations, they're very narrow composition ranges because they're based on the composition of the steel, whereas ASTM is always based on mechanical properties.
ASTM is based, and ASME is based on mechanical and chemical.
But they also oftentimes put chemical specifications in there. Not always, but oftentimes they do.
Okay.
Yeah.
It's
usually big. It's
like
usually big
mixing
ranges. It says you got to meet these mechanical properties, but you also have to stay within a certain range of chemistry. Yeah. Whereas if you look at 304 on the AISI side, you get very narrow ranges of allowable chemistry variations.
Okay. It was mixing and matching to me, so that explained it.
Yeah.
Okay. Different standard.
And confusing. Metallurgists like AISI.
Pardon me?
Metallurgists like AISI and mechanical engineers like ASTM.
Thank you.
Thank you. Okay. Any other questions or?
Yeah. Ah, good. Oh, this means I have to put on my glasses. All right, our next speaker is Devin Gonzalez. Devin's working on his PhD in metallurgical and materials engineering at the Colorado School of Mines. He's a Colorado guy, originated in Pueblo, and he studied welding and machining technology at Pueblo Community College. He earned both his bachelor's degree and master's degree in metallurgical engineering at the Colorado School of Mines. I did the same thing. I got all my 3 degrees there too. His master's thesis dissertation focused on developing metal matrix composite feedstock for electron beam additive manufacturing, and I mean that's a whole new area there. And he worked for Hazen Research, where he constructed and ran pilot plants for materials processing. Hazen's a pretty cool place, actually. He had an internship at Weber Metals, where he designed heat treatment cycles and mechanically tested aluminum and titanium aircraft forgings. And he has over 9 years of experience of welding and machining. So he sort of comes to this, by way of similar to John Steele, sort of getting interested in it by doing it and then working up into it. So he's a member of AWS, of course, and is actually very active in our local Colorado section, and a member of the Society of Manufacturing Engineers, SME, is American Society for Metals and Materials, ASM. Yeah. The Metallurgical Society, TMS, and AIST, and I don't know what that is.
That's the Steele Technology Society.
Yeah. Okay. His research includes non-ferrous alloys, additive manufacturing. This is a really big interest area. I mean, I see it everywhere. People are looking at 3D printing, but cool stuff like metals, right?
Yeah.
Not that plastic stuff. Advanced manufacturing techniques, high energy density welding, forging, and forming. So this guy's pretty broad based capabilities. So, all right, Devin, take over.
All right. Can everyone hear me? I told I speak very softly, so I'll try to speak up a little bit. I guess I'm going to take you home today, so I'll try to not keep you too long, make this as short as possible. So my talk today is going to kind of cover additive manufacturing in general and what we've done at the Colorado School of Mines to kind of advance the research in additive manufacturing. And I feel like additive manufacturing is, and I'll say it later in the presentation, but additive manufacturing is essentially welding. All the same processing and theory and quality controls apply to that. So I think this could be very well related to a lot of stuff. I'll be mostly talking about relating to aerospace applications, and I know that most of you are here for probably a D11 recertification, so this might be a little bit out of the norm, but a lot of these same these can apply to structural materials as well. So I think this could kind of cover a broad range of topics. So today I'm going to just give a brief overview of what is additive manufacturing. Then I'm going to focus specifically on the electron beam freeform fabrication process. That's actually what I did my master's on, and part of what I'm going to do my PhD on, but this one is really heavy in the aerospace industry, and it's for a lot of large-scale parts. So this would be the type of process that would be more related towards some more structural applications rather than the powder bed processes that a lot of people see from the small 3D printers. I'm going to talk a little bit about the feasibility of industry, how industry could implement additive manufacturing, and the research needs that still need to go into this to push it forward as a valid type of manufacturing process. And then I'm going to talk about our role in how we've kind of tried to advance the EBF3 process